First up today, Sonia Petrone talking about Bayesian UQ for recursive predictive algorithms.
Okay, thank you. And thank you to the organizers for the invitation to come at this very interesting workshop. Thank you to Isaac Newton Institute for hosting us in this program. And also thanks to you for attending the talk early in the morning. Not that early, but early enough. So this is joint work with my friend and colleague at Bocconi University, Sandra Fortini. What is the problem? In classic statistics, we all know, in classic statistics, prediction, so it's about prediction, of course. Its prediction is guided by a careful study of the phenomenon of interest from which we obtain, specify an inferential model, which in the Bayesian approach is expressed as x1, xn, given theta, have a conditional distribution P, given theta. Theta is treated as a random variable on which we express information through a prior distribution. And from this inferential model, can you hear me? Yes. And from the inferential model, we obtain, it's just applying probability rules, we obtain the predictive distribution, that is the distribution of the one step ahead. I will not say one step ahead. The predictive distribution of the next observation as in the formula. I think familiar. So the audience, I understand there are some Bayesian statisticians, but not necessarily. So I know these things will be kind of familiar to somebody, but maybe weird to others, unusual. So please interrupt me if there is anything unclear. So you see, naturally the Bayesian approach gives full uncertainty quantification on the next observation through the predictive distribution. However, there are many situations where specifying the proper model or eliciting the prior may be difficult. For example, in big models, the parameters lose interpretation, so expressing a prior is delicate. And moreover, the computations often, as we know, become difficult, especially if we have streaming data, so data that arrives sequentially. On the other hand, we see a wealth of predictive algorithms that I informally think of strategies to provide prediction with no explicit likelihood and prior. So there are many predictive algorithms that perform very well, but lack a full understanding and uncertainty quantification sometimes. So the plan here is, and what I would like to tell you is to show that by taking a Bayesian predictive approach, we may read a recursive predictive algorithm as a proper Bayesian predictive learning rules. So I interpret the algorithm as a Bayesian predictive rule, and then we can also understand whether the algorithm is implicitly using an inferential model. So we are used to go from the inferential model to prediction. Here we are going the other way around. And then if we can clarify the first two steps, then we can provide uncertainty quantification in the Bayesian setting. There are many examples and potential applications. In statistics, for example, using quasi-Bayes approximation of exact Bayesian procedures, and in machine learning. For example, there was what I found a very interesting, beautiful talk by Susan Wei at the recent workshop at UCL on post-Bayesian methods. And she was interested in using these things in understanding in context learning. The motivation I will give is, the motivating example for us is a statistical example. The problem is recursive estimation of a mixed distribution in a mixture model. We want to estimate G, and the data arrive sequentially. In the Bayesian approach, common, very popular, and very powerful model is to say, assign a prior with large support and non-parametric prior on G, typically a Dirichlet process. If you are done a bit of Bayesian non-parametrics, you know what it is. It's like a normal distribution in parametric, the Dirichlet process is the distribution, the basic distribution in Bayesian non-parametrics. But now it doesn't matter. The problem is that this model is very interesting, has a lot of applications and extensions, but the computations require MCMC or require variational base, but if the data arrive sequentially, then variational base is not enough. We should do some sequential variational base and so on. On the other hand, because we are at the Newton Institute, I mentioned Newton, but not Isaac, that's Michael Newton and his collaborators, time ago proposed an approximation, something that was a procedure that in the Bayesian non-parametric literature is referred to as the Newton algorithm for estimating G with recursively. And so the algorithm starts from G0 of theta. It's an approximation theta by theta. And so you might want to have this approximation then on a grid of values of theta. And then iteratively update and compute GI as the previous estimate obtained at step I-1 with a weight 1 minus alpha n. And then the second, this piece is when the current, so this is done with the first I-1 observation. When the new observation arrives, you use it as the prior and compute the posterior distribution, just updating your estimate the step before with the new observation. So when you have n observations and you propose Gn as the estimate, the point estimate of the mixing distribution. That's a point estimate, but what about uncertainty around it? Bayesians are used to give an entire posterior distribution. The point estimate is just a summary. And in fact, is this algorithm any Bayesian? Somebody studied it in frequentist term as an estimator, proving, like Sorju Tokar, proving frequentist properties, but the motivation was to approximate a Bayesian solution. So we studied it, and our question was, is this algorithm any Bayesian? So I'll go back to this example. Is that clear? Okay. That's the outline. The first step would be to give you some fundamental notions. So I mentioned we take a predictive approach. I'll tell you what I mean by that. I'll have to return on the meaning of the Bayesian predictive distribution. And then in the context of random sampling or of randomness, as Voloya Vodko was saying yesterday, what are basic desiderata for a Bayesian predictive rule. We'll see limitations, difficulties using exchangeability. We will go to algorithms or predictive Bayesian predictive rules that are asymptotically exchangeable. I will explain. And then when we will see that they underline an inferential model, and then we can do Bayesian uncertainty quantification on the unknown elements of the model through two techniques, either with resampling in what I will introduce, and maybe very familiar for some of you, predictive Monte Carlo, and also asymptotic Gaussian approximation. Yesterday we had 3 beautiful talks, overviews, very useful, very interesting. This is also somehow an overview, but we had calibration all the time. I didn't mention calibration yet. So I will get somehow to that in terms of predictive efficiency. Also, Volodya was mentioning efficiency, the word efficiency. There is not a clear idea what is predictive efficiency in Bayesian statistics, I think. Of course, scoring rules, and so I will give you the perspective that we are taking in this paper, but in terms of frequentist properties. Okay, so what is the Bayesian predictive approach? Sorry, I have to tell you what are, according to me, the main basic foundational principles of Bayesian statistics. Bayesian statistics originated from as a decisional theoretical foundation. In fact, one of the figures that I would consider really fundamental in its foundation is Ramsey. Ramsey was at Cambridge in the 1920s with people like Keynes, economists, and they were interested in founding a mathematical logic theory for agents that have to take decisions under risk. So the setting is very different from replicates of an experiment. They have to take a decision, they have some information, incomplete information, and they have to take decisions under risk. So your mind should go from replicates of an experiment to this setting. And then probability in this setting, trying to found a theory, a normative theory, comes as the prescribed tool to formalize incomplete information or uncertainty. So probability is the way we formalize our uncertainty. And should be expressed on observable facts, not right parameters, but observable facts. If we take if we go with these principles, then we see that the modeling effort is to assign the joint distribution of x1, xn, possibly for any n, if we think, as I will, that x1, xn can be extended to infinity in principle. So models can, I'm not against models, of course, they are very helpful, they may convey very good information, but are thought just as a ring of the chain that goes from past events to future events. So if we reason this way, we understand that we can directly specify, well, we can bypass, if we can, bypass models and priors and directly assign the joint distribution by assigning the predictive distributions, the one step ahead predictive, probability of x1, of x2 given x1, and so on. So we can, and this is the way, the predictive approach, to reason directly on prediction. Okay. So again, staying for a moment in the foundational part, what is the meaning then that we should, what is the meaning of a Bayesian predictive rule? Because I said that the principle is that information is expressed through probability, the evolution of information, that is learning, is expressed through conditional probabilities. That's another principle that immediately follows in Bayesian statistics. So the predictive distribution that I will denote by Pn is a learning rule. It formalizes how we learn on the next observation given the past. So it's not meant as a true generating process of the data. It might converge to the, if there is a true generating process, it might, as we get more information, might converge to the true. But its meaning is, it's a learning rule. It's expressing how we learn. That's why if we see a predictive algorithm, I anticipate, we can interpret it as a predictive rule. It's the way we learn. And so it will be very natural to think of it as a Bayesian decision rule. So any predictive rule in this sense is Bayesian. Any predictive rule that expresses through conditional probability how we learn on the future given the past is Bayesian. And notice that this is for a final sequence, but as I said, the chain of predictive distribution gives the joint that are the final dimensional distributions of the process xn as a sequence, in infinite sequence. And you can see that if we assign the predictive distribution, what we call the predictive rule, from any n, then we have all the final dimensional distributions of the process. Therefore, we define the probability law of the process. And this is the content of the well-known Ionescu-Dulcea theorem. So a probability law for a process can be assigned through the sequence of predictive distribution in a great generality. And so we see again that we can reason in a predictive way and understand the process. Mm-hmm. So what are basic desiderata? So I will now work in the setting of random sampling. And as I said, any predictive learning rule, as I said, is Bayesian. We are free, there are no constraints, but there are desiderata. And what are basic desiderata in the setting of random sampling? Random sampling from homogeneous replicates of an experiment. Randomness. The first is exchangeability. So it is not mandatory. Exchangeability is a probabilistic notion of interest in probability in many applications. What is the use of exchangeability for a Bayesian? Well, I have replicates of an experiment, and then it would be weird if my inference or my prediction depend on the order of the observation. Depends on the labels. I have patients and I consider them homogeneous. My inference shouldn't depend by their names. So I ask that the joint distribution is invariant to any permutation. And then if we have an infinite sequence, we ask that it is invariant under any finite permutation. That is permutation that only alter a finite number of indices. And this is a definition of exchangeability. P is exchangeable if its probability law is invariant under any finite permutations. So it's a desirable property. It's not needed, no? It's not that Bayesian means exchangeability, no, but it is desirable in this setting. It is natural. And then we want to check prediction with facts in many ways, but this is the basic minimal requirement, is that our prediction then agree with frequencies. So if frequencies go there, the prediction shouldn't be there. They should get closer as we get more information. And this property holds for exchangeable sequences, for example, as I will see in a moment. So we want that the distance between the predictive and empirical distribution converge to 0 with probability 1. Another, not requirement, but natural, desirable property is to see if, so this all is predictive. Is there any link with inference? If there is a link of inference, we would, on one hand, say, we would justify the inferential model based on probabilities on observable facts. And also we would allow inference. We would give back to our kind of more usual setting. So does PN is a predictive rule, it will be an algorithm. Does the algorithm implicitly use a model and the prior, say? So in the framework of exchangeability, these properties are satisfied. But first I said we reason on observable, we reason in a predictive way. So we assign the joint distribution through the predictive rule. And so what are the conditions on the predictive rule that ensure that Xn is exchangeable? Well, you know, the joint has to be invariant, so the predictive should be invariant to permutations of the past. It depends on the empirical, basically. But also, if we predict a future observation, K future observation, this predictive K steps ahead should be invariant, has to be invariant. So both of these properties are needed. It's an if and only if. Okay, so we have if we have a predictive rule, we can check these properties to see if we are defining an exchangeable sequence. Check with facts as anticipated under exchangeability. The empirical distribution converge. The predicted distribution also converge, and they converge to the same limit. The limit is random. The limit is a random distribution that I will denote with a tilde to remember it's random. So IID, you converge to, you have a Glivenko-Cantelli theory, converge to an F0, the true. Here, we don't know the true, we have a prior, we will have a prior. So it converges to, a priori we don't know, it converges to a random. This is with no information. Well, no, okay. That's the result. And then we also have the link to inference through the celebrated definite representation theorem, which says that if Xn is exchangeable, then P can be represented, informally speaking, as in terms of, well, then the sequence Xn is such that there exists this F such that the Xi given F are IID according to F, and F is random, and it's the random limit of the empirical or of the they have the same, of the predictive, they have the same limit. Okay, so This is general. Of course, in a parametric setting, this f could be indexed by parameters, so you have other information to restrict the f, the general f, to a parametric class. I will keep mostly this general notation, say, in this general setting. Predictive characterization. So what we see there is that, so what's the importance of the finite representation theorem? We reason on prediction, and we have the link to inference. So why Bayesian consider theta or f as random? That's why. Why a Bayesian model and not just IID? That's the reason. From exchangeability, we have the link to inference. And we see that the sequence of predictive distribution characterizes the law of the process. If the process is exchangeable, we have the underlying inferential model. Therefore, the sequence of predictive distributions characterizes the inferential model. So if we have an algorithm, we will be able to check if what are the unique model and prior that are used. These predictive characterizations have a long history in Bayesian statistics. Here is a famous example by Blackwell and McQueen, Polya sequences. You might be familiar with the two-color Polya urn. This is the generalization to infinitely many colors. And they define a Polya sequence as a sequence such that x1 has distribution p0, and for any n, the predictive is, let's say, a weighted average between p0 and empirical distribution, which is a very natural learning rule. And I show that in this case, xn is exchangeable, pn, no surprise because it's exchangeable, converge to a random f, and then this f, they find the prior. The prior is the Dirichlet process. This is a predictive characterization of the Dirichlet process. If you don't know what it is, well, it's the prior on the space of distribution that is characterized by this prediction. But the Dirichlet process, so if f is a Dirichlet process, that f is almost surely discrete, which has it's very interesting, has many applications and so on. But we might want to have a density. We might want to have f absolutely continuous with a density. So it might be natural to extend this, say, well, instead of a point mass here that then makes my f discrete, let's smooth it through a kernel, with a kernel. So my predictive distribution would be a weighted average, say, of this p0, maybe the initial density, and a sort of a kernel density estimate. But this breaks exchangeability. And and one would use mixture models for having a prior on densities. But then the computations are complicated, as I said before. So it's not easy to have exchangeability and a tractable predictive rule. And therefore, some kind of weaker forms of exchangeability become interesting. And I will focus on this property, asymptotic exchangeability. So exchangeability, as we saw, implies that the predictive distribution will learn the limit of the empirical. But the reverse is not true. So if I have a predictive rule that converges, this doesn't imply that the sequence is exchangeable, but it implies that it is asymptotically such. So it's a result in Aldous. These are the lecture notes of the summer school in St. Fleur, 1983. The Bible on exchangeability. So Pn converges to a random if my algorithm or my predictive rule is convergent to a random distribution, not to anything, it must be a random distribution, then xn is asymptotically exchangeable. So informally for n, what does it mean? Well, I tell you informally that for n large, asymptotically exchangeable is quasi-exchangeable. That is, xn given f are approximately IID according to f, and f is the limit of Pn. Pn converges at f. F is that limit, but it can be shown that also it's the limit of the empirical. So these are interesting processes also in probability. I'll tell you in a moment. Anyway, So we have the inferential, the Bayesian classical Bayesian inferential scheme with random sampling asymptotically for n large. So a sufficient condition for the predictive distribution to converge to a random f is that it is a measured value martingale, or in other words, that so this is equivalent to say that conditionally on x1 xn, each future observation has the same distribution. So I am at step n. My prediction for tomorrow, in 2 days, in k days, is always the same. This is a condition that has been developed. It's been introduced by Calibrating, but then developed by Berti, Pratelli, and Rigo in this paper. And there it's in the annals of probability interest because these are dependent processes for which the empirical converge. But for us, is a condition for having that Pn, that's a little n, converge to a random. And so it's asymptotically exchangeable. It characterizes a process that is asymptotically exchangeable. And indeed, there is a theorem by Calibrating that says that a sequence is exchangeable if and only if it is stationary and Pn is a martingale. So if we only ask the martingale property, we are breaking stationarity. We are imagining that there is some instability initially so we're somehow thinking of time. Our learning process at the beginning depends on the order of the observations, but this it's a very peculiar evolution because the data are identically distributed. For example, they are not conditionally IID, but they are ID. And so asymptotic exchangeability is telling that the process becomes stationary, so the order will not matter for n large, intuitively. So I go back to this example that I described at the beginning. So it's an example of a predictive rule that is a martingale. So the problem, you remember, was estimating the mixing distribution in a mixture model, and that was a Newton's algorithm. And then the questions we had, this is an estimate computed through an algorithm. If you think of the representation of a mixture model in terms of xi, theta I, so I have patients, the success of the therapy, and I have each patient has its theta. And then this is, in the Bayesian setting, also the prediction of theta for the next patient. It's still a prediction for theta, not for... But anyway, so the problem was... Sorry. The problem was, what about the uncertainty? That's just a point estimate. Can we have a full Bayesian uncertainty quantification through the posterior? Is this algorithm any Bayesian? Well, now we see that it's a learning rule. We are learning through the algorithm. So it's expressed through probability because that's a distribution. So, and we can interpret this as a Bayesian predictive rule. Here it is. The predictive rule that we are using for the x is this, where here is Gn, our estimate. So it's a way of learning expressed through probability. It's a Bayesian predictive learning rule. And we can show that it is a martingale. And what is its limit? Well, the martingale, the limit of this martingale will be the statistical model. We can compute it. We compute it, we show that Gn converge, and the limit of Pn is a mixture model with this G tilde, the limit of this predictive rule. Therefore, this algorithm is implicitly using an inferential model, a Bayesian inferential model that is asymptotically exchangeable. So only for n large, we can say that xi given g are IID according to a mixture model. And what is the prior? Well, the predictive distribution, where is it? Here depends on the data. So it depends on the sample path. It depends on the omega. It's random. And so we have a probability law on the x. So we have a probability law also on the limit, or it's the same limit that the empirical distribution is run as a limit the limit of the empirical distribution is random as a probability law. That probability law is the prior. So also here we have an implicit model, asymptotically exchangeable, and the prior. But we don't know what is the prior. It's implicit. And so the prior is implicit. Now we would like to say, I don't want only point estimate of G. I want an entire Bayesian uncertainty quantification through the posterior. But I don't know the prior. I kind of know the model because, compute the limit of Pn, it's doable. But I don't know the prior, I don't know the posterior. But they are implicitly there. And so, well, we have two techniques to approximate the prior and the posterior. We can sample from them, and also I will give an asymptotic Gaussian approximation. So this predictive Monte Carlo, that is something we used with Sandra, we proposed in this paper, but also is developed by Fong, Holmes, and Walk in this discussion paper, John Royal Series B. And they name it predictive resample. I'm used to call it predictive Monte Carlo. So it's a way for sampling from the prior or the posterior of the unknown quantity. So we were talking about mixture, but let's consider a general case. Suppose that Pn converges to F, random, and interest is inference on F. So it could be, I don't know, F my income distribution in a sample of individuals. Maybe I have a first stage of learning where exchangeability is not strict, is not exact, but then I have this asymptotic exchangeability, and I'm interested in F of t, the proportion of individuals below the poverty threshold. I always use this example. Or I might be interested in functional of F. For example, the mean or the quantiles. So we wanted to sample from the prior, which is implicit, or from the posterior. It's the same algorithm. We use the properties that I mentioned, that I described so far. Let's go to sampling from the posterior. So suppose that we have data, and we can generate an omega, because we said that the limit is random, the quantity of it is a random variable, depends on omega. The omega is the sequence, the sample path, x1, x2, and so on. So if we have an omega, say, then we would know the limit, the realization of the limit, and this realization of the limit would be a sample from the prior or from the posterior. So we can, but we have the predictive rule, so we can generate the omega in principle. In principle, the infinite sequence, x1n, here they are already given, and we go on, we generate what is missing in my omega, the future observation, in principle to infinity, in practice truncated to a large n. And then we can compute the empirical on this omega, say. Now we can compute the empirical of all the observation, the data, and the imputed observation that we have generated from the predictive. So we generate the first from the predictive, given the data, the and so on. And then because the empirical, we can compute the empirical with all the sample, or the predictive, they converge to the same limit. And then because Fn converges to F, and here n is large, this value will approximate F tilde of omega. It will approximate the limit, and the limit is a sample from the posterior. And so I have a sample of size 1 from the posterior distribution of Ft. And then if I repeat m times, then I have a Monte Carlo sample of size, an approximate, because it's truncated here, an approximate Monte Carlo sample of size m from the posterior of f of t. If I'm interested in a functional, then I can just, for each iteration, I compute the empirical, but also the functional, the realization of the functional for that sample path. So I plug in the empirical, and then I have a Monte Carlo sample from the posterior law of that functional. This is the approximation that if I am interested in the prior, Well, it's enough to start from 0. No data, I just generate x1 from P0, x2 from the distribution of P2 given x1, and so on. And then I can also have an idea of what is the prior. For example, in the Newton algorithm application, we use this algorithm in this paper. We propose this way of sampling from the prior, because here the interest is to see if the prior is a Dirichlet process, because Newton's algorithm was supposed to approximate the solution, the Bayesian solution in the Dirichlet process mixture models that are really very popular. And we find that, in fact, both through this sampling scheme and also through a theorem, we show that the implicit prior selects mixing distribution that have a density, I mean, they are absolutely continuous with the density. So the Dirichlet process is discrete. Although I think that they may be very close nevertheless, but anyway, and then that's the story. But it remains implicit. It remains implicit, and we can sample from it. But sometimes it would be useful also to have a direct analytic approximation of the posterior distribution. So let me just focus in the case where the predictive is a martingale. It is just a sufficient condition. The martingale property is sufficient for having that the predictive converge. It's not necessary. So we are in the setting I've been describing, is a martingale, does asymptotically, we have the model with an implicit prior. And then interest is again in estimating the proportion of individual below the poverty threshold, or that is FT, or we may also extend to the approximation of the posterior distribution of FT on a grid. We are working to find the posterior distribution of the entire process. But anyway, a computer will always plot you the posterior on a grid. And so this is, I will just look at the one dimension, it can be extended. So now what are we going to find is the posterior for n large is approximated by a normal distribution with center in the predictive, but with an asymptotic variance. It looks like a BVM. I'm looking at it looks by BVM as BVM, but it's not. Anyway, so remember that. Let's see if you have the intuition or how long I have.
22 minutes.
Okay, thank you. So remember that this F tilde, the unknown F, is the limit of the predictive. The predictive will know the F. So given data, we don't know the limit of Pn. We can compute the predictive, but we don't know its limit. So we are uncertain on F. I'm not saying there is a true F, not necessarily, there might be. I'm saying I don't know the limit of the predictive. I don't know the limit of the empirical, income distribution, limit of the empirical, okay. So what the posterior distribution of F is expressing is uncertainty about the limit of the predictive. It's usually thought as uncertainty around the true. And the two things must be related, but for us, in our perspective, and it is in the Bayesian perspective, the predictive is formalizing the uncertainty, the posterior distribution of F is formalizing the uncertainty around this limit of Pn, around the limit of Pn, that is around the limit of the empirical. So the asymptotic variance, the uncertainty in the posterior distribution will depend on the behavior of Pn. If Pn converge very quickly, even if I have just 100 observations, I will be pretty sure about its limit. If Pn is low, with 100 observations, I will be still very uncertain. So this is what is expressed here. We look at the way the predicted distribution learns from the data, which is also expressing how it varies. So we look at the predictive updates. No surprise here that predictive updates, I mean that these deltas appear. Pn is a martingale, so there is martingale story behind this. So we look at the predictive updates defined at point t, the poverty threshold. And this is the predictive estesso da delta. So it's how the predicted distribution in t varies in response to the new observation. This is computed with n-1. And and we consider this, well, these predictive updates will go to 0 because the predictive converge. So let's look at this quantity, where this appears, this quantity, and then we prove, so this is Vn, it's going to be the asymptotic variance, and it depends on the predictive updates. So we can show that, simplified story, formal description of the theorem under regularity conditions, the posterior distribution of f given the data, this is x1 equal little x1, xn equal, is approximately normal, centered in the predictive with this asymptotic variance. And this is true whatever, for almost all sample paths. So it's a result that also with probability p, the probability law of the sequence, equal to 1. So the normal is centered on the prediction, no surprise, because an implication of the properties I described is that the predictive is actually the expectation of ft given x1, xn, as it is under exchangeability. It is preserved, this property. So that's the center, and the asymptotic variance depends on the predictive updates. So depends on the way the predicted distribution learns from the data. And it can be extended to the posterior of f on a grid. So we can also, from here, compute asymptotic credible intervals for ft. So it will be, that's the... And we can see that the size of the credible interval, of course, depends on the asymptotic variance. So again, depends on the convergence rate of Pn. If Pn converges quickly, then again, at n equal 100, I will have fairly narrow credible intervals. Are you happy with this? But there is something else. So imagine a predictive rule that converges immediately. Basically, P0 and the predictive rule is constant. It converges immediately. It doesn't learn from... my confidence credible interval will be very narrow, but I'm not learning from the data. P0 is my prior guess on F. And it converges immediately. Pn is almost equal to P0. Then I'm not... So there is an issue here of convergence rate and learning rate. So I'm getting closer to say something kind of related to calibration. So so we not only want to see if the convergence rate is fast, but in fact we have to see if it is efficient, if it is also learning from the data. So there is an issue of balancing a convergence rate with a proper learning rate. So an issue of saying, okay, it should converge quickly, but also be efficient in learning from the data, with some notion of efficiency for which I don't have a solution, I will discuss. For example, again, if you want to look at this quickly, suppose that we have f distributed according to a Dirichlet process. Again, this was the predictive, P0, the empirical. We can rewrite it in a recursive form, the predictive at time n-1, and then this update when xn becomes available, and we easily compute the predictive updates. If you see the predictive update, it depends on this parameter. This is the previous predictive, and this is some kind of the learning rate in this recursive formula. And then suppose that alpha is large. If alpha is large, this will be very small, close to 0. And so if alpha is large, I will converge quickly, but to P0. I will converge quickly, but but I'm not learning much from the data. So when I have a new observation, if this is very small, the new observation doesn't tell me much. So I will remain basically around P0. So, so here is a plot. So here we are under exchangeability, it's a Dirichlet process. But we see the impact of this so-called scale parameter alpha. So the data are simulated from the solid line, which is a beta, and we see these are plots of marginal credible intervals, t by t, not even joint. But here alpha is equal to 1, and we see a larger credible intervals for a fixed t. Here we should see alpha is 100, fairly large, but imagine alpha equal 1000. And you see the credible interval is more narrow, but it doesn't include the truth. Maybe asymptotically we have good coverage of credible intervals with the Dirichlet process, but we see that the learning rate, or this alpha parameter, plays a role in tell. So it converges quickly, but doesn't learn well from the data, at least at the initial stage. Then it will go well. I would like to do something to not only have an asymptotic Gaussian approximation of the posterior. Remember that approximation is computed without knowing the prior. We don't know the prior. It's implicit, but we don't know it. Still, we can give Bayesian uncertainty quantification on the unknown f through the posterior. But we say, okay, it depends on how the predictive learns from the data. I want it to converge quickly, but also to learn efficiently. So what the notion of efficiency, how to evaluate it. So we are now evaluating the behavior of the predictive. And so we could use scoring rules. That's a direction I would like to take. I'm here to learn. I studied along many problems, but not in this problem, the scoring rules here. Let's see, because the approach is predictive, but we have the inferential model. Another way somehow to evaluate if my predictive distribution is learning well could be kind of related to the inferential model. So the plot I just showed you was telling about frequencies coverage of the credible interval somehow. So maybe a natural question is whether the predictive algorithm, I have a predictive algorithm, Newton algorithm, gradient descent, it's a natural language transformer, I don't know, and we are reading it as a Bayesian learning rule. We know, and now we show it as an implied model and prior. We don't know the prior, but we can approximate the posterior, but is this algorithm learning well? And it is natural, from what I said, to think that, we could ask if this algorithm has good credible intervals that also have good, asymptotic credible intervals that have good frequencies properties. That is in particular, that has, getting tired, that has good frequencies coverage. And so this is a way to evaluate. Now we look at the frequencies properties. We imagine there is a true F0. And we ask, is the predictive algorithm giving me credible intervals with good frequencies coverage? So now, under exchangeability, coverage is usually granted by best and for Mises kind of results. So these are saying that for n large, if the data are IID according to true distributions of p theta 0, then the posterior distribution of theta is asymptotically Gaussian, centered on theta 0 or on an efficient estimator, and the asymptotic variance is the inverse of Fisher information. But this is under exchangeability. First of all, we just have a martingale, or maybe even we just have a convergent predictive rule. I just saw a paper recently, it's an archive paper by Edwin Fong and Yu, where they work on best and for Mises theorems for a specific class of predictive distributions. So beyond exchangeability, not asymptotically exchangeable. Our approach so far has been, well, we gave a result that is not a best and for Mises theorem. because our aim was just to approximate the posterior distribution under the law of the Xn. So we have an implicit model, an implicit prior. We want to compute the posterior distribution analytically, but we don't know the prior, and this is an approximation. We didn't study frequentist properties so far. It is just, instead of using MCMC or instead of using predictive Monte Carlo, I use this approximation. As I'm approximating my posterior distribution. So this is a kind of DUB, it's a probability one result. It's similar to, it's a refinement of DUB theorem. DUB theorem says that the predictive distribution, the empirical converge to the limit, the asymptotic variance goes to 0, and then the posterior distribution is cumulating around the limit, F0, say. We also say that what is this asymptotic variance, how the variance goes to 0, and then we are saying there is a normal distribution. So we like to say it's a refinement of the theorem. It's a fundamental theorem in behavioral statistics, you might know. And moreover, in best and for Mises theorem, the asymptotic variance is expressed in terms of the variance of an efficient estimator. For us, is expressed in terms of predictive updates. So it depends on the quality, on the capacity of the predictive rule to efficiently learn from the data. So what I was hoping to have these results clean and ready to be presented. They are too preliminary, sorry, for being presented, but we have some results where we give conditions on the predictive updates such that a DUBVM nickname holds, so that we have that the asymptotic variance is related to the predictive updates, but is also related to Fisher information. And so in this case, we would have with probability 1 asymptotic credible intervals with good frequentist properties. Not for any F0, roughly speaking, only for the F0 or theta 0 in the support of the prior, very roughly speaking. Anyway, so I can stop here, or if you want, I go quickly through this last example, because I mostly consider the sort of no parameter, it's just a general case F. Here is a last example where we apply these things in a parametric setting. So this is classification. We want to model, so X are features, Y is 0, 1. We say we model like this. So with this G could be a neural network, could be a logistic. In fact, we are going to take the logistic, but it can be complicated. And given a training sample, we would do Bayesian inference, would treat beta as random, assign a prior, compute the posterior, or often we just estimate beta by minimizing a loss function. I think this is, oops. And again, a computational cost may be expensive if we have many features, and also if the data rise sequentially, because anyway we have to repeat the computations from the beginning. So a popular way to go is to use online gradient descent. And again, you see we have a recursive rule. We start from beta 0, and then we recursively update beta n, our estimate. Here we consider binary cross entropy loss, a logistic function, and then this would be our updating rule. So it's parametric. So then can we read it as, is there any Bayesian predictive rule? Well, here what we are saying is that the probability that of a 1 given the data and xn plus 1 is, so that's a predictive of the next y given the x. And here we have the gn. So and then this is again a context of random sample that's stochastic. Xi, yi are in principle would be exchangeable, the pairs. So we also have to say something on the distribution of the xi. Here, for simplicity, assume they are IID according to marginal. So we actually are in the framework I just described, the predictive distribution for the next pair given the data. Now, in this setting, we can prove that Bn converge to a random beta. It is itself a martingale, this helps. Not needed, but here it helps. And so Pn, the predictive distribution, converge, this is a consequence, converge to a random f. That's a random f on xf, xy, such that, what is this f? Well, it is such that we have an quasi-exchangeable, asymptotically exchangeable model with an implicit prior on beta. Yes? So we have the predictive is given by, these are just IID, and then we have this predictive, the predictive rule from online gradient descent. This converge to a random parameter in this case, and then the joint predictive of the next pair converge, and this random f is a joint, is such that the conditional is like this. Moreover, this Bn, so there is an implicit prior, and this is the implicit Bayesian point estimate that we have. And then we can do inference even if we don't have the prior. So sometimes people say this is Bayesian inference without the prior. There is in fact an implicit prior, but it's all implicit. We would like to do sampling from the posterior of beta, but notice that here we would need to sample both the x and the y, because this is a predictive for the pair. Oops. This is a predictive distribution for the pair. So we would need to sample pairs, but we don't know px. So here, really, the Gaussian asymptotic approximation is useful because we couldn't do direct predictive resampling because we don't know the marginal of x. And then again, we can give a sort of a normal approximation of the posterior for n large, where again this v depends on the predictive updates now expressed in terms of the betas. And you notice that this depends only on what happens in the sample, and it also doesn't depend on the unknown px. So this is... Okay, so I think I will stop here, and thank you very much for attending the talk.
I think we've got time for a few questions. Talia.
So the BVM theorem, you do it under the assumption the model is well specified, or can you do it for misspecified models?
We don't. We just say we take the algorithm as it is, and then we say this algorithm, is it any Bayesian? Well, it is Bayesian in that sense. It implies a model. It implies the prior, and we say, in fact. In principle, except when I get to BVM, I'm not assuming any existence of a true. It is just a learning rule.
So you express the variance, for instance, in terms of the prior and the likelihood somehow, but you don't assume anything about the true distribution.
No, because so I go back to this result. Our idea is that so Bell-Stanford for Mises theorem, frequentist properties, as you teach me, they are in the literature study looking at properties. Well, the likelihood is given usually, except for work in misspecified problems as yours, but usually it's taken as well specified, and then one looks at fine details of the prior. So it's very frequentist now, it's fine details of the prior. Here I'm trying to be as Bayesian as possible, as genuinely Bayesian as possible, reasoning, that is for me, the Bayesian, the predictive approach is natural, is the approach, no? So, and I'm not trying to necessarily to estimate a true. I'm just trying to learn from the data. So I would like to find, do BVM for the moment, and maybe BVM theorems, where the assumptions are given on the predictive. So that would be more interpretable for a Bayesian, more interpretable maybe also in machine learning, because in machine learning people have algorithms. In artificial intelligence and larger language models also. And then wouldn't maybe be so interested on the true, but if I learn well. So having BBM, for the moment for us BBM we don't know,
My question really just was because, you know, the Bayesian inference from a specified model doesn't behave asymptotically efficiently, right? So my question
it would be,
really was,
that's a good suggestion, thank you. I didn't think about this, yes. But anyway, I would be happy to use more genuinely predictive criteria. So this is a way to go, look at frequencies properties. This is natural because after all we do have an implicit inferential model, and frequencies properties are natural and important. It's embarrassing if I have a plot like the one I showed, narrow credible interval, and the true is outside, no? Because because I'm simulating, there is a true. But perhaps finding some more predictive criteria, so really go through, generally saying I would like to also explore another direction, find appropriate scoring rule and calibration, and again I'm here to learn from you all. There are some references if you like here. So maybe this statistical science paper is a review paper where all these stories are presented.
Okay, let's thank Sonia again.